Right. I'm Adrian. I've been an Apple engineer for Apple products for such a very long time. Come through Objective-C and now into Swift. And today we're going to cover sequences in Swift, how they work, and how you can use them to improve your code both in readability and performance. So let's have a basic look. So I'm sure you've all seen the for-in structure that you use for for loops within Swift. There used to be C-style for loops, but they were removed long ago in Swift 3. So now we're left with the sequence structure. So in our for-in loops, we provide it with some sort of container which conforms to the sequence protocol. And for every iteration, we pop out an element that we're going to work with. So it's just a quick example with sum. We've got an array being iterated, a range, and then a dictionary, which is passing out the key and the value. So the actual protocol is pretty simple for sequence and iterator. A sequence has an associated type which defines an element, which is the element that will be returned. And it defines an iterator, conforming to iterator protocol, and it has a function to make that iterator. The iterator protocol, even simpler, the same associated type, and then it has a function that returns the elements as an optional. So at the point where all your elements have been consumed, it will return nil, and that will be the end. You should know it's marked as mutating because the iterator might contain state, and as we iterate through, the state of the state of that iterator is going to change. It's mutating. So let's have an incredibly trivial example. We're going to make an iterator that iterates through all of the lowercase Latin alphabet. As you can see, we defined our element as character. We've got a private position, and then in our next function, we have a guard to make sure that our position is less than 26 characters in the alphabet. We're going to defer incrementing our position, ready for the next iteration, and then we're going to make a character to return. To consume that iterator, we create it. As I said, next is mutating, so it's a variable. And we're going to use a while loop in this case, calling next, popping out to value at the points that it's finished, value will become null, and then the while loop will finish. As you can see, we're not using for-in because that's an iterator, and for-in uses sequences. To make it a sequence, we wrap it in sequence. You can see we've made it a sequence. We're making that iterator returning that alphabet iterator, and then we can use our for-in loop. Very simple. The majesty of sequences comes in its extension methods. So there is a huge number of extension methods that we get within our standard library that provide all kinds of handy functionality. So we've got ones for checking if sequences contain elements, if they all satisfy a specified condition, if the elements within two different sequences are equal. We've got functionality for finding the min or max element. We can get the prefixes or suffix, or we can drop parts of it. There's all kinds of functionality in there. We can sort, we can reverse, we can shuffle, and then goes on. We can split, we can join, and we also have the higher order functions, which provide common functionality like producing a copy of a sequence as an array where the elements have been filtered based on the predicate. We can map to a new array based on the content iterated for each one. We can compact map, which is just like a map, except it will strip all of the optional values. We can flat map, which will take a nested sequence of a nested set of sequences and flatten them down into a flat level array. And then we have reduce. And we're going to quickly run over reduce because we're going to see it a few times. So the idea of reduce is it takes a sequence, consumes all of its elements, and then produces a final single object for it. So in our contrived example here, we have an array of integers, and we just want the sum of them. So in our for-in example, we're defining a sum variable. For each iteration of the element, we're adding it to the sum. We can use the reduce method below. We're specifying in the first one the default value of 0, which is what would be returned if the sequence was empty. And then you see we have this closure taking in a partial result in the element and returning them added together. We can simplify that even further for cases such as add, where we can just specify the plus operator. As a first aside for an obvious handy tip for sequences, like every other type in Swift, can be extended. So if you've got functionality such as calculating sum, extend sequence and add that functionality, and then it can be used everywhere. So in our case below, as we've extended sequence, we can now sum up a range or a closed range or any kind of sequence, not just array in this case. Just one more I want to quickly note, because it's going to appear a couple of times as well, is the concept of enumerated sequence. So in our example for sequence, we have a function in its extension called enumerated, which returns an enumerated sequence wrapping that initial sequence. And then when we iterate through it, we'll not only get each value from that initial sequence, we'll get it in a tuple with an index. And that's just the count going through that iteration. So 0 for the first element, 1 for the second one, right through to the end. And that exists for all kinds of subranges. So even, example, as array slice, you get the same concept where we just return in the middle of that array and still get that 0, 1, 2 index. An incredibly handy additional functionality for sequence is the concept of being lazy. I love being lazy. So we have an extension on sequence, lazy, returning a lazy sequence. Lazy sequence conforms to lazy sequence protocol. There's not a lot to it. A lazy sequence protocol, which you could probably guess, is a sequence, and all it does is it contains a particular other, it wraps another sequence. That's all that actually exists in extending sequence in itself. But what it does change is its extension methods. So we've got a whole bunch before. The following ones are overwritten. So for a standard sequence, all of these functions, extension methods, when you would call them, would return an array. So it would allocate a copy of all the, allocate memory for a copy and populate that array with all the contents. For our lazy example, the return values for these are replaced with what's called lazy adapters. And we'll have a look and see how this works with a patented, contrived example. So for the first 1 million positive integers, how do you find the first and the 100th even number, which when spelled out contains the letter V? Yeah, contrived. So in our non-lazy example, I would do it this way, to be honest. I have our range with our first million integers. I'm going to filter them to find which ones are even. So if they're a multiple of 2, and then going to map them to take their integer values and make a spelled out string. And then I'm going to filter them for which ones contain V. I'm going to take a prefix of those first 100, and then I can get the first and the 100th value, which is the last one. The issue with this, as you can see in this little comments, is the amount of work it does. So for every filter map operation, it is going to entirely consume the preceding sequence, and it's going to allocate an array containing all of its values. So for that first filter, we're going to run that test on all 100 million, all million integers, and we're going to return an array containing all 500,000 even integers. We're then going to take those 500,000 even integers, and then we're going to spell each one of them out. So we're going to have an array now of 500,000 strings. We're going to filter them, and at this point, we're actually then going to get a copy of our array containing 300,000. Is it 64 of them? Yeah, so for each one of these, we've allocated all that memory. And then for our prefix, thankfully, an array has an efficient way of representing subsequences. So it's going to return an array slice. So mercifully, no memory allocated there. And then we'll be able to get our first and last value from that array slice to get our answers 12 and 726. What does the prefix do? Oh, sorry, prefix returns the first 100 values. Yes, so we'd have what we got, 300,064 long array. That prefix is going to return a sequence that's just those first 100 items. So our first element that comes out is that first index, and our last one out is that 100th one. Why did you here multiply integer for multiplication of 2? Oh, sorry, I want to get the even numbers. So I'm testing, so I'm filtering them to get the ones that are a multiple of 2. Hey? Is that part of the problem? Yes, I just wanted the first 100 even numbers. Yeah, that contain a V. If I was to now use our lazy sequence, as you can see, the outputs of each of these has now been changed. So we've added our lazy property, and we have wrapped our range event in lazy sequence. As we call filter, we've wrapped that range in a lazy filter sequence, but we haven't done any work. We call map, our lazy filter sequence is wrapped in a lazy map sequence, but we still haven't done any work. We're just wrapping constantly. Filter again, we're going to wrap all that in a lazy filter sequence. And our prefix is essentially again wrapped once more. We've done no work at this point. It's just completely wrapped. When we call our first and last now, we're going to massively reduce how we work. So we're now going to bubble it up through each one of those operations using the iterators to get them out. So when we call values.first, we're going to get the first element from that prefix. The prefix doesn't have anything, we've just wrapped. So we're going to call to the filter to get the first that begins with V. There isn't anything in it, so we'll call up to map. We need to spell it out, call up to the first filter. So the filter then comes up to the range, which gets its first number out, which is 0. And then we run through the test. Is it multiple of 2? Yes, we'll spell it out. Is filter, does that spelled out 0 contain B? No, it doesn't. So we then move back all the way up to the top, pop out 1, work through filter. Of course, isn't a multiple of 2. So we go back up to our range, pop out 2. And then we go back through filter all the way down until we get to 12, which contains V. So then we can return our first. And we do the exact same thing for last, going through constantly until we get to the 100th item, which is 726. But when we call first, we've done that operation, calling our filter 13 times, map 7 times, filter 7 times. When we do it again for our last one, we're going to do all of that work again. It's not going to remember we reached 12, so it's going to repeat that work. It's completely ephemeral. Every time you try and access any element within lazy, it does all of its recalculation again. So if you want to keep that information so that you can constantly query it, it's a fairly simple example. You wrap it in an array. So at this point, we have now created an array of strings that contains 100 items, and we can query our first and last or any other values in those 100 at will. But again, we haven't had to repeat that for every element. We've only done enough work that we have to do to get those 100 elements. So we've massively reduced both the time we spent processing to spell out and the amount of memory we've allocated. Right. So if we just quickly come, because we're going to run through collections quickly, we've seen sequence. We have a structure of what inherits from it. So we have collections, which can become bidirectional and random access collections, which we'll cover. And then we also have mutable and range replaceable collections, which add some concept of mutability to collections, but we're not going to cover through them today. So we understand the potential limitations for sequence. They're potentially ephemeral. So a sequence has a concept of an iterator that we can iterate through, but there's no guarantee that you can iterate through it repeatedly. So you imagine opening and reading a file. Once you reach the end, if you try to carry on reading, you just get nothing. Whereas the concept of an array being a collection, you can repeat through it multiple times. Same with, as we saw with our map and other things, any operations that we perform on it to get subsequences of things will always produce array copies. So we're always going to allocate arrays, always going to allocate memory if we want to deal with sections in the middle of sequences. And secondly, we can't do anything with that sequence without iterating it. So we can't query its count without potentially consuming it. We can't get elements within the middle without consuming it. That's corrected by collections. Collections now guarantee that we can consume it repeatedly. We have the concept of efficient subsequences, like we saw with array slice, and we can query the count or various sections within it, because as we can consume it repeatedly, we're able to query it in any way we wish. Collection extends sequence, but also adds a couple new associated types. We have the idea of an index, which is a way that we can uniquely address an element in the collection. We have indices, which is a collection of those indexes. And we have a subsequence, which is going to be a collection representing a portion of our sequence, but backed by the original collection. So we're not going to allocate any new memory when we get to it. The actual required extension methods for a collection, we have a subscript to get the content out of our collection. We have a start index and an end index. So the start index represents the index that would be for the first object in that collection. The end index is the one that's past the end. The reason it's that way is that we can simply test that if the start index and the end index equal each other, the collection's empty. We have a function that when you pass in a specific index, it will return the index after. And we also have an inline form so that rather than making a new copy, we can pass in one and it will be modified for the next index. So if we take our alphabet sequence, we can now conform that to collection. As you can see, we've still got our character element, but we've now specified an index being int, our start index exactly as it would be, and you imagine an array, its first index is 0, and its end index is 26 because it's one past the last character, which would be 25. Our subscript allows us to get the actual character out. And as you can see, we're just using the operation we had to calculate what the character would be from that position. And then we have our index after, which we're just making sure the index we pass in is below this end index. And if it is, we're just adding 1 to it. So we can implement 1, 2, 3. And as you can sort of see an example, this is how an iterator works for collections. So if every time you run through iterating, it calls index after to get the next element. And it will call it index after and after and after until it reaches the end index. And that's how indexing works, why we don't have to specify an iterator for collections. We have a default type called indexing iterator. The question being that we've seen the concept of indexes and elements. What do we do for things that aren't ordered? So arrays are nice and simple. They have a specified order. You can imagine that they're going to be iterated through ordering. I have sound. So sets, pretty simple. The element that comes out of the iterator is going to be the element in. Dictionary, less so, because as we iterate through, we get the key and the value. Obviously, when we address elements in a dictionary, we address them by their key and we get the value out. So why do we get both? And what order or anything do we get for set? Because sets don't have orders. We don't even index them or query them in particular ways. We just test if a set contains an element and we can insert and remove. Well, there's no particular compile magic for iterating for elements. The element for a dictionary is a tuple that contains that key and that value. The reason being, the element specifies what will be returned when you iterate. So it might sound weird, but when you're defining a collection and a sequence and things like that, what you're defining with the types, the associated types, is what will be used for iteration. So even though we as developers treat a dictionary as containing elements or values that we access by key, when we're iterating through them, we get both. Same with the index for set and for dictionary and set. The types are dictionary.index, which is weird and pointless to us. What does that mean? Well, it doesn't mean anything to us. It's arbitrary. It's what the language can use to efficiently iterate through them. So for each of them, those index types are actually a variant. And as dictionaries and sets can have 2 backing implementations, they can have their native Swift one, or they can have a Cocoa version from Objective-C. That determines how they're going to be indexed for iteration. So for its native version, both of dictionary and set are backed by this internal hash table type. And that's the index that it's actually going to be used for iteration. It's just a way for the iterator to know how to efficiently access that element. So if you're interested in that, the hash table index just contains information about the bucket that the elements are stored in. Same with the order. The order, it doesn't matter for these elements. It will just be how they're inserted into those buckets. So there's the potential that when you insert something, so you add a new key into a dictionary, when you iterate through it again, it's not necessarily at the end. Same with a set. When you insert something into a set, when you iterate through it again, the new elements aren't necessarily at the end. They're just there at the position they would be for efficiency. And that's the idea of iteration, is that it allows you to get every element out of its container or out of its collection. The order is determined by how logical the storage is. And if your collection is sorted as it is with an array, you'll get them out in the expected order. If they're not, then it comes out in the order that's most efficient. Just a quick note on, as we mentioned, for some useful things that will appear later for collection. As we can now iterate through it multiple times, we add a count property, so we can now query the count. The efficiency for that is order n, because the actual default implementation literally works through calling index after, counting through the various indices until it reaches the end. So it's the length of the collection is how long it takes. Is empty queries the start and end index. So if they're the same, the collection is considered empty, which is why it's a constant time. And that's why if you're going to need to query if a collection is empty, it's always recommended to use is empty. One, it's not only easier to read and clearer, it's more efficient. And then just a note, as it will appear later on, there's now a convenience for just collecting the first element. So if the element contains something, collection contains anything, that first element variable will return it. Just a quick note as well on subsequences before we get to the interesting stuff. As I mentioned, the idea of subsequences is an efficient backing. So if we were to get this slice subsection out of this particular array, what's returned is not a new array, it's what's called an array slice. And that array slice is backed by that original array. It contains a a reference to it. It doesn't allocate any new memory for those 4 items. It's just calling back to them. And as such, the indices follow through as well. So for an array, as you can imagine, the first element of an array in this example is A, which is index 0, index 1 is B, index 2 is C. For that slice, that array slice, we have those same indices. So our first element, we return B, because we're getting the middle out, but it's still using that index 1, and then index 2 and index 3. However, we are testing range. So if we were, even though it still exists in the original array, if we were to get index 0 of that subarray, we'd get a compiler error. So it's an important thing to remember when iterating through is don't try and second guess, unless you have very good reason, what the indexing system is going to be. You want to just use the default iterators and use first and last and offset. So you can call index after first index to reach a specified offset rather than just assuming that everything's always going to start at 0. We saw collection. We have bidirectional collection, which adds the reverse. So as we had index after, we now have index before, so we can now iterate backwards. A couple of nice advantages of that. We now have a constant time last. If you wanted to get the last index of a collection, you would have to iterate through all of it until you reach the end. Whereas this, you get a constant time because you can just get the index before the end index. Even nicer, we have an optimization for reversed. So in collection and sequence, our reversed function will make a copy of all of its contents into an array, and it will then reverse that array. So that's an order n operation. For bidirectional collection, as we saw with lazy, it's wrapped in a reverse collection. So if we were to make a reverse bidirectional collection, no work's done. We just wrap it, and then as we iterate through it, it will be iterated backwards by that reverse collection. It just wraps around it.
Is there also a reverse function of that D that sorts the or reverses the array without making a copy?
There is in yes, there is in mutable collection. So there's a set of overrides or a set of custom newer functions defined by mutable array that allows you to do in-place things. The last we're just going to quickly cover is random access collection. It doesn't add any new functionality or any new methods. It just provides a promise of performance. So for, like as we saw with our count, and also functions to get the distances between 2 indexes, they in sequence collection and bidirectional sequence are order n operations. So we keep working through index after until we know those values. Random access collection guarantees to do it in constant time. That's just essentially, the random access collection is just a performance guarantee for types so that you can
enforce that.
No, it's no actual enforcer. It's just essentially a guarantee. If you're given a type that's random access collection, the implementer has assured to you that striding through it is a constant time operation. But there's no actual functionality beyond that, and we'll see why that matters shortly on. Right. So we're going to quickly move to unfold sequences. We saw with our alphabet sequence that we can write a sequence, but we can also use these 2 unfold sequences to easily make sequences by passing in states and closures. So we haven't got to deal with that boilerplate code. So we have 2 that exist in the language. We have one that has a state that we can modify that allows us to track iteration. And we have a second one that's an optimized form for usage that allows us to specify the first value of the sequence, and then a closure that allows us to take that value and then calculate the next one. And as it loops through, it will keep being applied with the previous example until it's time to reach now. And we'll see an example of that in a moment. So for the first one, if we have this example of a sequence to generate Fibonacci codes, we've got all our various boilerplate for making it a sequence and making an iterator, but our main content's in the middle. We've just got our state, which holds essentially the next 2 elements in that sequence, and then our next function will calculate what the next 2 after that will be and return that first value. Let's see, it's a lot of boilerplate making that iterator and that sequence. We can just wrap that in an unfold sequence and just keep that middle bit. So you see, for our state we're passing in, we're defining those first 2. And we've got our interesting section for calculating the next state and returning them just in line. So we can do it that way. In our slightly contrived example for the first one, our first example, if we have a situation below where we want to just double a number each time. We're specifying that as the first value, and then our next closure is just taking that value and then timesing it by 2. So it's similar to the while loop above, where we're just keeping a reference to the previous one and then timesing it by 2. Contrived, but a slightly less contrived and more useful example is that you can do it for moving through the view hierarchy. So if you've got a view, UI view, NS view, and you want to move through your view hierarchy to the top, you can keep querying its super view and move through. And the advantage of doing it with sequence over while loop above is we get all of the nice extension methods. So say you want to iterate through your view hierarchy and only query for a view of a particular type. You could use complex map to make sure that that view is of a particular type, or you could check if it's an accessibility element of markers, or if it's been given or not given an accessibility label. And you could use filters to do that so that you can more efficiently in unit tests or such thing be able to make sure that all of your code is actually correctly labeled for accessibility. There are a couple of specialized types as well that are just handy to know about. So we've got the concept of an empty collection, which is always empty and immutable, and a collection of 1, which is always going to contain 1 element. They are both handy in situations for optimization and also clarity. So if you have a situation where you have code that needs to take in a sequence, but you always want that content to be empty, rather than just generating an empty array, which is going to allocate memory, if you pass in an empty collection, it's not going to actually allocate things. If we quickly look at its implementation, it doesn't do anything, as you can imagine. It implements everything for random access collection, but there's nothing in there. Next always returns nil. Its start index is 0, its end index is 0, its count is 0, and everything's inlined. So at the point where if you use this, there's a good chance that the compiler can actually see that there's nothing happening and completely eliminate that code. So places where you need to deal with iteration but always have empty content, there's a good chance your compiler can just wipe it out by using collection of 1, by using empty collection. And similarly, collection of 1, slightly more code, but the same basic concept. Rather than allocating memory, you've just got a single variable for that element. The getter and setter just points to that element. Its count is always 1, its index is always 1, its start index is 0, it's always 1 long. So again, a lot of the checks and functionality can be wiped out by the compiler by using these. And going from that, let's just quickly look at the idea of consuming a sequence. More contrived examples. So let's say we have this function to calculate the sum of primes, and it's taking an array of integers. It's pretty simple. You've got an array there of the first 6 integers, and we're going to calculate the sum of primes. It takes in a sequence, fine. It takes in a reverse sequence, fine. However, if we do this and put it into a variable before, we get a compiler error. As you can see there, it's expecting a reversed collection. Why? Well, the answer is simple. We saw with bidirectional collection, we override reversed to produce a reverse collection. The reason the one above works is because even though we override it in bidirectional collection, that's an overload of that function. The original implementation, the sequence that returns an array, still exists, and it fits the signature for that method. So the compiler goes, oh, I can't use that one, but the original sequence implementation works, and it will accept it blindly. So if you have that first one going, what it's actually doing is it's going to use that original, take that array, make a copy of it, and reverse it in line. And it's going to do all that work, and you might not even realize it because you haven't noticed that it's stripped away that optimized form. If we take a slightly different example with prefix, which returns an array slice, that one's always going to fail, but you've got the same issue because it's going to return prefix returns an array slice rather than an array. So the way we could fix it is how we fix lazy, by wrapping it in an array that then fits the conditions. The problem is, as we've just been with reversed, all the performance advantage of having those subsequences in an efficient manner, having that efficient bidirectional collection is wiped out doing this. You've made a new array where you're allocating memory and putting the contents in. We don't want that. That's pointless. It's the waste. So instead, we're going to do the opposite way. We're going to change the signature for the method. We're going to just, rather than forcing it to be an array, which is how most people consider writing code by default, I need to take in an array of integers. We're going to change it to take in any sequence that has an array. By doing this now, our errors are wiped out. If we were to do it inline, we'll always get that reversed bidirectional. Yeah, I'll always get our reverse collection and our prefix accepted. And then we can take it for any type. So that empty collection we saw now works. The collection of 1 works. we don't even need to have it as an array containing all the numbers. We can just pass it a range and you get the exact same result. So by doing this, we enable us to not only have more flexible code and more expressive code, but we can also keep all the performance benefits we get from using these optimized types. So a quick shout out to the Swift algorithms package. We saw before the number of extension methods in sequence. Swift algorithm adds loads more. So many useful ones, and it can be merciful that I'm not going to go through them with you, but I am just going to call out a couple because we're going to see most of them later, and another one I like. So we're just going to cover chain first. So I don't know if any of you have ever written code that looks like this. I definitely have, where you've got an array of elements and you want to iterate through them and an additional final element. I've done this in places where I've got, for example, some sort of decorator that needs to appear at the bottom, like I've got views that I need to set the color for, and I've also got a final footer view that's not in the main array that I need to color as well. In this situation, as we saw before, we're putting another element in an array, so we're going to allocate an array with memory for that. When we add them together, we're then going to make a copy array, allocating memory for all of it, just to iterate through it. Well, we can use chain and collection of one in situations like this. So the chain function will take in two sequences and iterate through them, one after the other, without allocating any of the memory. So we get massive performance improvements by just avoiding that allocation. Another one, just to mention, because we're going to just briefly see it later, is the concept of windowing, which is showing how we can improve our code by using algorithms within sequence. So the idea of a windowed sequence is essentially you get a subsequence in a set size that you step through. So in our example, we're getting a window of 3 for this, array and range example. And you see we're getting the efficient subsequence type for both. As we would iterate through it, see it just takes 3 each time until it gets to the end. It's very handy for situations where, for example, you've got triangle strips, let's say, where you've got code that's content that's going to repeat, and you need to keep the previous example while getting the next item. A more common example of that is generally with 2. So there actually is an optimized form of this called adjacent pairs. It does the exact same thing, but rather than return a sequence, you get a tuple of the first and second element. So it's very handy in situations where you need to keep the two going through together. And that's the one that we'll see later on. And the last one, just as a reference, because we'll use it again later, is index collection. Exactly like we had with enumerated, but rather than a count, it returns the actual index. So this one functions on a collection rather than a sequence, and you get the actual index for that item. We'll see why it's handy later. Let's have a look at the concept of striding dates. So Ellen has her date talk across the way, and we'll have a look at why this is handy. So we have the idea of a stride, and so it's stride to and a stride through sequence within Swift. So if you have a situation where there's a lot there, but where if you need to step through a set of numbers by a set value, you can do that using stride. So in our example, we've got a double, and we're going to stride from 0 to 100 by stepping by 1. So you can get 0, 1, 2. Below the same example where we're going to go from 100 to 0, reducing 1, so 100, 99, 98. Same with stride, going from 0 to 2, 0 to 100, stepping up by 2, and then just an arbitrary double value where we're going to step through these numbers by an arbitrary number. That's very handy for situations like this. And you can conform anything to stridable. Date itself conforms to stridable. So you can see we can step through by 60 seconds. But that's just it. We step through by seconds. Very handy if you want to step through something that's a definite fixed period. Not handy for working with real dates. As Ellen will tell you, dates are hard. You can't step through by a day. Days aren't the same length. You can't step through by a week. Weeks aren't the same length because days aren't the same length. Months don't even have the same number of days. Years don't have the same number of days. It's difficult. So the way we get around it is by doing calendar arithmetic. And we can essentially make a copy of stride that does that. So let's have a look at an example of, we've now here got an example of a function called stride date. And we're specifying that we're going to stride through by days, forwards or backwards, or weeks or months or years. And as we're producing sequences, we once again get those extension types. So we can then filter. So in our example here, we're going through between 2 dates, stepping through a day each time. We can filter to check if they are a weekday, and then we can map it to the start of that day, or we could do a bunch of other things, test into it. So we can do complicated maths, complicated date-based striding, really simple by wrapping the concept of moving through days within a sequence. You can see, as we saw before, we've got the same example where I've just defined a stride date for striding and striding through. We're passing in the date components that we're going to stride by, and we're passing in a calendar option in because not everyone uses the Gregorian calendar, or not every device is set up to use the Gregorian calendar by default. And if we look through, the base implementation isn't really important, but the idea within the iterator in our next is we're testing what way we're going because we're going to go forwards and backwards. But the actual calculating what date we're going to return, we're just using that calendar and adding our stride amount to the date, and we'll just keep repeating it till we reach the end. And so now what is actually quite tedious calculations for trying to get a set of dates, we can reduce bound to just using a sequence, specifying our start, end, and our stride, and then we can apply and use all the sequence methods with them. We're going to have, example now, another contrived example. This one becomes contrived recently because we're going to do it sequence, or I should say recently, but it's contrived for me recently because we're going to do it synchronously. The reason I say it's contrived is this isn't actually how you would do it. And following through from Dan's talk this morning, which you're always learning things, there is an asynchronous implementation of this, and it ships as part of the standard library for URL, and you can asynchronously iterate through lines of a file for any URL. And I didn't actually realize this existed until after I'd produced these slides. You're always learning. But we're going to have a look at the concept of doing it synchronously just as an example. It's contrived. So if you try and search how you actually iterate line by line through a file in Swift, you obviously get Stack Overflow as your first Google result. And it recommends you do it this way. So you have your URL. It recommends you read that URL into a string and you split it by new lines. That results in you reading the entire file into a string and then producing a set of arrays for each line, an array with a string for each line. That could be massive. So in this dictionary of words example, there's 236,000 words. So you're doing megabytes of work to get this content in just to be able to iterate through it line by line. So we're going to write a file that write a function that lets us read in files by a line. And we're going to use unfold sequence. So we're going to do it with a closure. Now, it looks like we've got a lot of code there, but it's not really. And we're going to just step through some of the important parts of it. So as you see, we've got our unfold sequence. And you see we're just specifying a sequence. We're going to return a string where we've got lines, and we're going to return nil when we're done. Our state is actually just going to be a pointer to a file. So we're using fopen, fclose, one, because they're quick, and two, because they're short and fit on the slide. It's arbitrary. Yep. So it looks more complicated than it is by using them with our unsafe mutable pointers. And then we've got our code that reads our line. So you see, if our get line actually contains contents, we make a new string from that C string, trim the end lines off it, and we return it. If not, we close the file, and that's it. And now we have our sequence, and we can consume that sequence as we want. And of course, it's a sequence, so we can do all of our lovely lazy and filter and map things. And it's going to read it one at a time, rather than having to pull that entire file of 236,000 words in, and then filtering them for just the ones that contain ADE, and then capitalizing them and then pulling them out. We're going to do it line by line. So we've got a huge memory improvement there by not reading it in. Now we're going to do something slightly weird. We're going to make a sequence of recursive elements. So let's take this example of just an arbitrary recursive structure, so a file system. So you've got files, and you've got folders, which can contain files or folders. Recursive structure. Just to show you how we're going to represent that, we're just going to use an enum. So files have got names, folders have got names, and then they've got children. As you can see, we've just overridden children for convenience, so that a file's got, it just returns an empty array in this case. Just for brevity. That same tree we saw has just been converted to the actual enums there, just for completeness. So let's say we want to, in an arbitrary example, gather all of the names for all of the files and folders recursively. I mean, you could do it in a traditional manner by just writing a function that takes in a file item and then recursively calls that function repeatedly to gather those names. So it first makes an array that sticks the name of its item in, and then for each of its children, it calls gathers names. And for each of those children, they'd call their children gathering names, returning out. The end result is you end up with an array containing all those names. Obviously, in the middle, you're going to have multiple array allocations as you gather those items, building it up, going through. I mean, that's fine. It's not particularly Swifty looking. So we'll make it an extension just to give it the best chance. So we've got the same code, exact same structure, but now gather names is a property and we're using flat map. It's going to use the exact same code, exact same functionality. But I say we want to do sequence things and we want our code to be usable. And say, if we were to extend for our system item to have file sizes and we wanted to do the same, getting the sum of the file sizes, we then need a new property or a new function to go through and gather them. So we're going to make a simple recursive sequence that allows us to wrap recursive structures into a sequence. And we can see the sort of end structure for how this is going to be. We're specifying an element being the file direction. We're going to specify the key path for its children. And then we can use all those lazy and map and filter and everything functions that we have before. So let's have a look at the base level of what the entirety of the code to do that is. So we're defining a sequence called recursive sequence. It's got two generic types for base and S1. So that base element is going to be a base sequence, as you say, is a sequence that contains the root elements. And then that S1 type is the type of sequence that contains all the children. The reason they're different is because for convenience. So potentially you could have a situation where the children are contained in a set or some other sequence, and you don't want to have to force it into an array. For our iterator, we're doing it in a standard depth first style, so we're going to make a stack. So we have a stack, we're going to pop our elements into it, we're going to pop one off. If it's got children, they get popped onto the stack and we return them. And we keep working through that stack until they're popped out the end. It's a fairly standard depth first search way of getting elements. As I said, we've got our base sequence because we can have multiple items at the top level, you think, such as a table view. So if we've only got one element, we can use a collection of one rather than an array as our top element. And that's why we've got two different versions. So our base element can now be a collection of one rather than forcing that into an array. And then now we can completely consume a recursive structure using this recursive sequence. So we specify the item going in and its children key path, and then we can do that. We can take it one step further. We can actually conform file system item to sequence, have it return the iterator for recursive sequence, and then we don't even need to wrap it. It already knows that its key path is going to be children, and then we can call map and lazy and filter and everything directly on that item. We can go further, to be honest. We can conform it to collection. So we've got a bit more code here, but as you can see, what we're doing is our index is now going to be an index path, so that we actually can track, going through its children, how we would reach that item, exactly as a table view would use. So you'd have an index path specifying the table, the cell within the table. We now have conditional conformance though. So before our base sequence and our base collection conform to any kind of sequence, they now conform to collection, because there is the possibility that we need to iterate through them multiple times. Same as we're limiting the index type to index for each of them. The reason being we're using index path as our index, so we need those indices to match. We're setting the start index, which is just 0, and we've got our end index, which is going to use the count of base. So the end index, if we've got one item in there, it's going to be 2, because that's past the end. For our getting the item from getting the element out for that index path, we're going to walk the index path using sequence, because we can. So we're going to make an iterator for that index path and pop off each one of those items and then walk through getting the initial item by its index and then working through getting its children, getting that index and working through until we reach the end. And incidentally, that's what this reduce at the bottom is doing. It's essentially a hack, because sequence doesn't have a last function. So what this reduce is actually doing is it's taking the initial one as its example, and every time it's iterated over, it's replacing it with the new value. So effectively, you are just, by doing this system, you can always get the last element out of a sequence without having to maintain some particular variable above it where you can track. And of course, we can do, again, so we can then also we'll need to get the index after. So we've got slightly more code here, but we're doing the same thing, a similar thing, where we're going to walk through that recursive structure If it's got children, that's going to be the index. If it's got a sibling, that's then its index by appending the one by one. And if it doesn't have children, it's going to then have to work its way back up. Interesting point that we'll get to in a minute is the complexity for this, and we'll cover that in a moment. And we can take it one step further, the exact same thing to make it bidirectional. So we can perform it to bidirectional collection by being able to iterate through the index backwards. But it doesn't perform to random access collection, as we can see by performance. So its index after and its position, they're not constant, they're log n, because we have to walk that array. It's very much not the distance. Our count is order n as we walk through it. Its distance is n log n, because we need to find a particular element and then we need to walk back through it. So we don't meet any of the criteria for performance for random access collection. So although we get all those lovely benefits, we can't guarantee that because it's not random access collection. So we document that in our documentation, saying that it has this performance limitations, but it's still a collection. It still functions in this way. And now it conforms to collection. We can go slightly further. We can now do more complicated things like printing with depth. So we saw our indexed function from the algorithms. We can use that index path because obviously each part of that index represents how deep it is. And we can convert the count -1 of that index to a tab. And we can tab its name in, map that to and print them out. And so we get it to print out its own depth in the tree structure. And we can search and get an index path. So we can try and find the first element that's a file containing PNG and get the index out, the index path out. And then we can go even further and we can extend our recursive sequence to take in an index path and get all the elements along that way. So now in a situation, we can pass an index, map it to name, and get out an array of our names of all those elements. Right, now, so we've seen that we can do that with extending or making sequences to deal with recursive structures. We're going to quickly make a container. So we're going to make one from scratch. So we're going to make a 2D grid and show how we can make collections that are useful to us. So 2D grid is just a 2D array. We've got the idea where we're specifying width and a height for our grid, and we can access things through a point with an XY coordinate. So sin 2, 1 is 8 in this example. It's actual backing storage because it's just an efficient way to do it. In our example, is we're just going to use a 1D array. The idea is not that we're doing anything profound in our storage. We need to just represent a 2D grid. And so we need to expose for our collection that concept. So our backend storage can still be 1D, and then we've got functions that convert between a 2D coordinate and a 1D position in the offset index of that 1D array that we can then use. If we conform it to collection, fairly standard. We've still got our index being that 2D point. We can use the default iterators, indices, and subsequence. Our count is obviously going to just use the width times the height. The elements is just going to defer back to elements because it's convenient. Our start index is 0, so 0, 0 in there. And our end index, we're just going to use the count, which would be the past one index, the end index for our array, and then convert that into a 2D coordinate. Same with our subscripts. We're just going to convert them from 2D to our 1D offset for elements. And same with our index after. We're just going to use those two functions for movement between 1D and 2D representations of index. And we can do the exact same thing for bidirectional and random access collection. So we can conform entirely to every functionality. And that's fine. So as we'd iterate through our grid, we'd go from 1 to 36 going across by default. But we can then take the idea that we're making custom collections and go slightly further. So we can make a sequence or a collection that conforms to a subgrid. So as we had for our subsequence, we can have a logical subgrid. So we can have a collection that takes its grid as a backing store, but has a smaller size that we can work through. So we can have a 3x4 here. And again, it's just using its same indexes, deferring to the original base for its position. And it's just got a custom index after to calculate when it should end or when it should move to the next one and where its end index is. And again, we just add an extension to grid that uses that, as you can see. So now we can call subgrid origin 0 width 3, 4, width 4, height 3 to get that item. And obviously rows are just subgrids, but just one high and width long. So we've now got row functionality. The same with column. we can take our concept of windows that we saw before, and we can make a windowed operator for it. So we can have a windowed sequence for our subgrids. So we could iterate through all the columns. We could iterate in a window style through subgrids. So if you've got situations where you are dealing with, I don't know, let's say you're going to have some sort of particular game where you need to analyze the content around it, you could window through that content to get to it. You could do slightly further. You could do it with borders. So this example, the implementation is in the materials on the subgrid, but you can create a sequence that calculates what all those border points are and then iterate through them. So you can have it. So if you just need to know the edge, you can have a sequence that returns all of those to iterate through. And you can make as many as you want. And again, you can have it arbitrarily sized. So you could have it, so you specify a point and get all the elements around it. And if you want, because it makes a difference, you can make it wrap. That could be part of your border sequence. And the implementation for this is in the materials, it's in the Discord, but I'll give you the link if you want it as well. And then from there, you can do fun things. So you can make game of life. It's an incredibly simple amount of code now. So we can get the indices, which are obviously the point for each. We can then use reduce to reduce that into a new grid of the same size. Its default value, but the initial value, which is going to be 0, which is dead for Conway's game of life. And then we can iterate through each one of those indices, get the border around each one, which will wrap around, used our sum, which we wrote right at the beginning, which was that original reduce, to get the count that are alive. If there's 3, our new point is going to be 1. If it was 2 and the old version was alive, it's going to be 1. And then we can step through, and we can have that functionality in place. So we could do it with very little code by producing collections. We can get all this complicated behavior where we can introspect all of our views. And now I promised art. So for our one final thing, we're going to make a spirograph. So I'm sure you've all had a spirograph as a child. If you're not entirely familiar with what it is, it's a big cog with a small cog inside it with a pen in it. And as you spin the pen around, moving through this cog, it draws lovely spirals. It's more dull in its particular example. But there's the maths to produce it. And as you can see, once again, unfold sequence. So we're specifying our state is just our offset as we're moving around. And for each one, we're calculating the X and Y point for the next position. And we're adding theta for our next one. And we'll just iterate through it. And this will go forever. But obviously, if we're going to draw a picture, we don't really want it to go forever. So with our implementation, we use prefix. So we want the first 100,000 points. We're using lazy because we don't want to retain everything. And we're going to map it by a scale and a pan. It's arbitrary just to make it a nice size. And then we're going to reduce it into a path. And you see in this example, we're taking in the first element. We're making a path, and we're moving the point of that path to that position. The reason being, if we just added a line, it would draw it from an origin, it would look weird. And then we're accumulating beyond that. So for every line after that, we're adding a line to that path, so it will draw around as it goes around. Now, I haven't mentioned that first reduce. That first reduce doesn't exist in the standard library. So we write it. It can be our own extension. You can write whatever extensions you want. So in this particular example, for reduce, we're making the iterator for our element. If it has a first element, we're going to pass it to that first closure and get our result element that we're going to accumulate into. And if it doesn't, we return nil. And then for every other element, we call our update accumulating results, and we build it all up in that way. So we're building it up in that particular way. But again, we can extend it slightly further. We can add our conditional conformances, as we saw before. So if our sequence contains CG points, we can add that as an extension to make a path for us in that particular way. So now our code just becomes that. And we can just go for our final one all the way. So we can then have this. So in this example, we're doing the exact same thing, taking our first 100,000 points and mapping them to a nice position. But then we're using our adjacent pairs to get them in 2s. We're going to map that to add a line. So rather than accumulate it together, we're going to make a line between each two sets of points. We're going to enumerate. So we're going to have an index for each one from 1 all the way to, I guess, 99,900, from 0 to 99,999. We're going to map to lazy again. Seems weird. The reason being, enumerated does not return any kind of lazy sequence. Enumerated does not conform to lazy. So we need to call lazy again. Otherwise, our next map will produce an array with all our content. So into our map, we're going to receive that index for that count from enumerated and the path. we're going to take that index that we've called it, we're going to calculate a hue. So we're just going to have an arbitrary color value that rotates around every 255 points all the way across the hue scale that wraps. And then we've got our hue and our path. And our final step, we've got our CG context, and we reduce it into that context. We can use that path to add it to the context, set the hue color, we stroke it, and it draws, and the final element now is the entirety can be just reduced into an image. And we can repeat that for every single one so that we can actually animate our image as we go around. And so we can build up incredibly complicated functionality just by chaining all of these functionality together. So, this is a summary. If you have functionality that you can repeat, obviously generalize your algorithms. It's recommended for everything. But if you've got sequence functionality, such as sum, as we saw, such as that repeat first, make them their own algorithms and you can reuse them. If you're writing custom containers, conform them to the sequence and collection. You'll get all the benefits of the sequence extension methods and all the ones that appear everywhere else. And you'll be able to write cleaner, more understandable code. Generalize your input parameters. Don't make everything that needs to take a particular collection an array. Allow it to be sequence or collection or whatever the most generic type is, because then you can keep all the optimization benefits that come from the further down protocols such as collection or bidirectional collection. Be lazy. Be lazy everywhere that you possibly can be. If you're going to chain multiple methods together where you're going to filter in a map, by using lazy, you're going to be able to do them. You're not going to allocate memory for each step. Take advantage of all the functionality that's provided to you everywhere. So all of the concept Swift algorithms, those empty collections, the collection of one, there's various other things that exist. Use them and you'll be able to have performance benefits without having to produce your own code. The one final warning is profile your code. That should be advice from every single speaker is there may be weird conditions you have. Profile your code to make sure that it actually is performant and you understand the performance penalties and improvements from using these various techniques. And then you'll be sequencing success. Thank you very much. Is there any questions?